It's a perfectly quiet morning beneath Mount Rainier. Dawn light spills over a snow-clad summit, and far below the peak's shadow lies a patchwork of farms and suburbs. There's no hint of fire, no ash drifting in the sky, no rivers of lava. School buses roll along riverside roads, and hikers fill the trails. In every way, it's just another ordinary day in the shadow of the volcano. Yet the experts are on edge. Volcano scientists quietly admit Mount Rainier is among the most dangerous volcanoes in America. The United States Geological Survey calls Rainier the most threatening volcano in the Cascades. Geologists are frank that a future Rainier eruption or collapse could dwarf the infamous 1980 eruption of Mount St. Helens. Why? Part of the answer lies in people. Tens of thousands of Washingtonians now live atop Rainier's ancient mudflow deposits, and those numbers continue to grow. In fact, about 80,000 people and their homes sit directly in Rainier's Lahar hazard zones, ground that was buried by prehistoric mudflows. Some planners estimate as many as 2.5 million residents live in the 6 river basins drained by Rainier's glaciers. In many Puget Sound towns and valleys, children play, farmers sow fields, and commuters drive their cars without a second thought to the ancient forces slumbering above. But beneath that normalcy lingers a spine-chilling question. How can a perfectly quiet volcano become America's deadliest? No one hears volcano tremors or sees smoke. Yet scientists whisper that Rainier's greatest danger isn't in the eruption column, but in what the mountain could do quietly. Beneath the mountain's snowy cap, Mount Rainier is rotten inside. Intense heat and acid-rich fluids have been stewing rock for millennia. Volcanic gases and superheated water have percolated through Rainier's core, gradually turning solid lava into slippery clay. Hot, acidic groundwater can convert hard volcanic rock into weak, clay-rich rock, explains the United States Geological Survey. Over centuries, the summit itself was literally dissolved. Geologists say the former Mount Rainier peak was decomposed to clay and weakened by hot volcanic gases and solutions, until huge flanks collapsed away. Today, the cliffs and headwalls high on Rainier remain heavily altered by these fluids. Blocks of grey rock are stained orange, yellow, or green by sulfur and mineral reactions. Scientists have mapped vast zones of clay-rich rock along Rainier's upper flanks. On the volcano's western slopes, above the Puyallup and Nisqually drainages, entire sections of the cone are laced with loose waterlogged clay that evolved from deep hydrothermal activity. In places you can taste the acidity of the air. Hot springs bubble with sulfur. This chemical weathering isn't obvious on the surface, but deep inside Rainier the rocks are weak and water-saturated. What's more, a massive ice pack presses down on that weakened interior. Rainier holds more than a cubic mile, approximately 4.2 cubic kilometers, of glacial ice, as much as all other Cascades volcanoes combined. Over time, those thousands of feet, hundreds of meters of snow and ice add tremendous weight. The glaciers slicken the slopes, lubricate loose debris, and even form hidden lakes behind temporary dams of ash. When that ice melts, by a bit of heat or by rain, it can instantaneously flood valley bottoms with millions of gallons, millions of litres of water. In other words, the mountain is quietly aging and weakening. Its core is rotting, and its shoulders are overloaded with ice. A catastrophic collapse could happen at any time, even when the volcano is otherwise dormant. This hidden decay is a shocking twist. We often picture volcanoes as fiery magma chambers and flowing lava, But Rainier's deadliest transformation is a silent one. Geologists have painstakingly mapped layers of mud, boulders and logs in all the river valleys around Rainier. They show that Rainier has produced multiple giant mud flows in the past, completely burying villages that once stood there. In effect, history is proving the threat. On the mountain's south side lie the remains of long-ago events. Before the giant Osceola flow, at least 3 older lahars roared down what is now Paradise Park. 2 of these, the Reflection Lakes and Paradise Lahars, blanketed the Nisqually Valley with tens of meters, tens of feet of debris running at least 38 kilometers, approximately 24 miles, downstream to the town of National Washington. Trees growing today at Paradise still lie buried in orange, yellow and red clay from those events. Imagine the scene. Long before Seattle existed, rivers of wet mud, hundreds of feet, dozens of meters, deep, rushed out of the mountain, burying forests on the valley floors. The granddaddy of them all was the Osceola Mudflow, about 5,600 years ago. This was Rainier's signature collapse. A massive chunk of Rainier's eastern flank, roughly 2 to 3 cubic kilometers, approximately 0.5 to 0.7 cubic miles of rock and ice sheared away in a ferocious avalanche. The summit lost 1.8 kilometers, approximately 1.1 miles, of height, leaving a horseshoe-shaped crater as wide as the one at Mount St. Helens after 1980. That enormous debris avalanche quickly turned to slurry and swept down the White River. It flowed over 100 kilometers, approximately 62 miles, nearly to Puget Sound, burying the landscape beneath hundreds of feet, dozens of meters of mud. Today, the remains of that 5,600-year-old lahar underlie dozens of towns. The suburbs of Kent and Auburn, parts of Puyallup, Sumner, Orting, Buckley and Enumclaw all lie atop Osceola's deposits. Everywhere you drive in these valleys, you are literally on Rainier's mudflow, evidence that the volcano already ran its red light through this region once. About 2,600 years ago, Rainier collapsed again on its west flank in what is called the Round Pass mudflow. This sector collapse removed a chunk of rock near the Tahoma Glacier headwall, visible today as a large depression. The jolt sent a surge of mud racing 30 kilometers, approximately 19 miles, down the Puyallup River Valley, damming tributaries and leaving hummocky deposits as much as 30 meters, approximately 98 feet, thick. Part of this flow even spilled into the Nisqually drainage toward National. In places along the Puyallup, these ancient boulder fields can be over 90 feet, approximately 27 meters, deep, relics of that prehistoric landslide. Shortly afterward, during a large explosive phase of Rainier, around 2,200 to 2,300 years ago, the National Lahar formed. A violent eruption melted snow and blew rock into the headwaters of several rivers, mixing hot debris with ice. One branch of that event rushed down the Nisqually Valley at least 100 kilometers, approximately 62 miles, to the Longmire and Ashford area. It was one of the most voluminous flows yet, triggered by classic pyroclastic melting. But it's noteworthy that this lahar, like others, travelled far beyond what most people imagine a volcanic mudflow should reach. Perhaps the most telling case is the Electron Mudflow, only about 500 years old. It began with an avalanche high on Rainier's west side near Sunset Amphitheatre, not from an obvious eruption, but likely from a crack, an unseen explosion, or even a nearby earthquake. Vast volumes of clay rock gave way, turning instantly into a flow of water, mud and boulders. This lahar was incredibly fluid and fast. It ploughed 100 kilometres, approximately 62 miles, down into the lowlands, reaching present-day Puyallup Valley towns within an hour. When it reached the Puget Lowland at Electron, a small town, the mud was 30 metres, approximately 98 feet, thick, burying entire forests. Later studies even found buried tree stumps near Orting under 20 feet, approximately 6 metres, of mud, victims of the electron flow. In short, that event has left its mark on modern-day neighbourhoods. Even the name Electron reminds us of that buried past. Across all these crime scenes, the clues are unmistakable. Rainier has done this before many times. Geologists scoop up bits of sediment and wood, radiocarbon date charcoal, and map the extent of old lahars. They find ringed wood, log jams and boulders polished like river stones, all testify that giant flows once roared here. We don't need imagination or speculation to know the risk. It's been done. In multiple valleys, lahars have already buried towns. Many of those ancient mudflows were powerful enough to scour and then reshape entire valleys. But here's the tragic irony. Those same mudflows created the communities now at risk. The valleys and basins where people settled were formed by past eruptions. Flat, fertile floodplains of volcanic sediment drew farmers and builders just as much as the soil attracted nature's bounty. In fact, the town of Orting, population approximately 3,300, sits entirely on Lahar Fill. It occupies a flat basin between the Carbon and Puyallup rivers, ground that was under hundreds of feet, dozens of metres, of mud only half a millennium ago. In Orting's green fields, llamas graze peacefully, but below them lies a graveyard of old-growth trees engulfed by the Electron Lahar. An old saying among locals is that they are living on the volcano's graveyard. Orting's residents know they are in harm's way. Indeed, geologists have nicknamed it Rainier's Ground Zero. But it wasn't always a disaster zone. The same lahar that buried Orting also left behind thick layers of sand and silt, which over the centuries became rich farmland. Similarly, downstream towns like Sumner, Puyallup, Buckley and Auburn are built atop the loamy sediment of old mudflows. Highway bridges and rail lines now run along channels that once carried debris hundreds of feet, dozens of metres deep. In other words, the volcano's own devastation created a fertile flood plain that humans gravitate toward. Settlers poured into these broad valleys, laid orchards in the rich mud, and erected cities on the levelled ground. The very attributes that made these locations attractive, flat terrain, abundant groundwater from glacial melt, thick soils, are the spoils of former lahar disasters. In a cruel twist of fate, the valley that was emptied by lahars is now cradling houses and schools. It's an ironic legacy. The volcano's past violence levelled the land, and generations later people built on that land, sometimes with scant awareness of its deadly history. Today, Orting and its neighbours work to remember what lies beneath. Signs warning of lahars dot the roads. Sirens and evacuation drills are part of community life. But the geography itself, and where populations have grown, is the bigger shock. Beneath countless Washington yards is the volcanic mud of Rainier's prehistoric floods. Emergency planners often describe Mount Rainier's greatest danger with a single number: 30 minutes. That narrow window begins the moment a lahar is detected. Across Rainier's river valleys, an extensive warning network stands ready for exactly this purpose. Acoustic flow monitors buried along key drainage channels continuously listen for the unique ground vibrations produced by fast-moving debris flows. If a major lahar forms, those sensors immediately relay the signal through emergency communication systems. Computers activate warning sirens, emergency alerts are transmitted to mobile phones and radio stations, and local officials begin evacuation procedures within seconds. But detection is only the beginning. For many communities built on Rainier's ancient floodplains, the available evacuation time is measured not in hours, but in minutes. Pierce County emergency managers estimate that some areas could have as little as 30 to 40 minutes to reach high ground. A simulation by the United States Geological Survey found that a large collapse from Rainier's west flank could send a lahar into Orting in less than 50 minutes. Earlier planning documents frequently adopted 30 minutes as a practical benchmark because it reflects how little time remains once warnings are issued and people begin moving. That half hour must accomplish an extraordinary amount. Thousands of residents must recognize the warning, understand that it is real, leave homes, schools, businesses and workplaces, and travel to elevations safely above the valley floor before roads, bridges and low-lying neighborhoods are overtaken by a fast-moving wall of mud, water, trees and boulders. This is why emergency planning around Rainier focuses less on vehicles and more on walking. Traffic congestion can develop almost immediately, while designated evacuation routes lead directly uphill to predetermined safe zones. Every minute spent hesitating or choosing the wrong route reduces the already limited margin for escape. The challenge extends far beyond individual households. Schools must account for thousands of students. Hospitals and nursing facilities require specialized evacuation procedures for patients with limited mobility. Businesses must rapidly move employees while maintaining clear access for emergency responders. Even temporary road construction, bridge maintenance, or unusually heavy traffic can significantly affect evacuation times within such a compressed window. Recognizing these realities, communities beneath Rainier practice regularly. In March 2024, more than 45,000 students and staff from dozens of schools participated in the largest lahar evacuation exercise ever conducted. In Orting alone, approximately 13,000 students walked nearly 2 miles, approximately 3.2 kilometers, to higher ground, rehearsing the same routes they would use during a real emergency. The exercise demonstrated both the effectiveness of repeated practice and the enormous logistical challenge of moving entire communities before a lahar could arrive. The warning system surrounding Mount Rainier is among the most sophisticated volcanic emergency networks in the United States. Yet its greatest limitation cannot be solved by better technology alone. It cannot create more time. That is the defining challenge of living beneath America's most dangerous volcano. The mountain may provide only a few tens of minutes between the first unmistakable warning and the arrival of one of nature's fastest-moving disasters. Every siren, every evacuation drill, every marked escape route, and every emergency plan exists for a single purpose: making those 30 minutes count. Everybody assumes a volcano's deadliest threat is a dramatic eruption. But Rainier can kill without blowing its top. In fact, an enormous eruption would be likely heralded by earthquakes, steam explosions, a growing bulge, but the scenarios we fear most involve no Big Bang at all. It can start with a strong earthquake far from sight, shaking loose the rotten summit. Or a massive chunk of clay rock on the west flank might simply give way under its own weight, Scientists point out that many old lahars began this way, with a landslide or collapse when Rainier was quiet. For example, the 500-year-old Electron flow apparently was not caused by any recorded eruption. It likely began as a debris avalanche, perhaps triggered by a small, undetected steam explosion or tremor down a slope weakened by years of hydrothermal alteration. Likewise, even the Osceola event may have been hastened by volcano-driven rockfalls. In short, no fiery magma eruption is needed for Rainier to send a lahar hurtling out. A collapse high on the flank is enough. Other culprits are Rainier's own ice and rain. Imagine an exceptionally warm spring day, or an intense cloudburst. Torrents of meltwater can suddenly surge. In the mid-2000s, scientists noted that very heavy rainfall or rapid glacier melt can produce debris flows on Rainier almost annually. If an unusually hot thermal spring boils a glacier from below, the sudden floodwater can entrain rock and slide downstream. Historically, small eruptions with no warning have caused lahars simply by melting snow and ice, and today extreme weather might do the same. With climate change, summer thunderstorms on the volcano's stripped slopes could theoretically trigger a large lahar out of the blue. Even Rainier's hydrothermal system itself can instigate collapse. Glacial destabilization is a concern. If heat from below melts part of a glacier's base, the stored weight of ice can release and torrent downhill. Or long-term chemical alteration may already have formed hidden clay pockets that just need a nudge. Since we know Rainier's hazards arise from gravity, water and weak rock, the key point is the mountain doesn't have to explode to cause disaster. A spine-chilling realization emerges. If an earthquake or slide suddenly frees the altered rock on Rainier's slope, the mountain could spit out a deadly mudflow with no volcanic eruption first. That phrase, "no notice lahar," is increasingly common in emergency circles. To understand how water and ice can top magma in danger, we look beyond Rainier. In fact, the deadliest volcanic catastrophes in history often involved lahars, not lava or ash. On November 13, 1985, the Nevado del Ruiz volcano in Colombia had a relatively modest eruption late at night, but the volcano was capped by snow and ice. Within 3 hours, heat from the eruption melted the summit glaciers, sending walls of mud some 30 meters, approximately 100 feet, high down the slopes. Those hot, fast flows obliterated the town of Armero. 70% of its people died, and killed over 23,000 residents in Armero alone. Across that night, lahars engulfed villages, carried cars and homes in turbulent slurry, and transformed towns into graveyards. It was Colombia's worst natural disaster of the 20th century. As one scientist later noted, Ruiz proved that a relatively small eruption on a snow and ice-clad volcano can produce lahars that threaten populations many tens of kilometers, many tens of miles away. The tragedy of Armero was not fiery lava, but freezing mud. One of the iconic images of Ruiz's event shows an empty street in Armero, Colombia, buried under brown mud. Houses are flattened and uprooted. A truck is lying on its side. The caption reminds us how close safety was on the higher ground, yet unreachable in time. It's a visual testament. Volcano plus ice equals disaster, even without massive lava flows. Other examples abound. In 1991, Mount Pinatubo explosively erupted. Through excellent monitoring and evacuations, only about 700 people died from the initial blast. But over the next years, rains and melting snow created hundreds of lahars down Pinatubo's rivers. Half a world away in New Zealand, Mount Ruapehu's crater lake famously burst its dam twice in the 20th century. The 1953 collapse unleashed a massive lahar down the Whangehu River. Sadly, a passenger train was crossing a rail bridge in the Tangiwai Gorge when the lahar swept the bridge away. 151 people were killed in that Tangiwai disaster, not by ash or fire, but by the muddy flood that followed the lake's collapse. Afterward, New Zealand installed an automatic lahar alarm, laws, to protect against the next lake outburst. Even at Mount St Helens, 1980, which is famous for its blast of ash and rock, the biggest loss of life was from the immediate pyroclastic avalanche rather than lava. Only 57 people died overall, far fewer than Ruiz or Ruapehu, and one reason is that Mount Rainier, with its vast ice cap, has far more potential water. The lesson from all these is clear. The deadliest volcanic disasters often involve water, ice and gravity more than magma. The good news is that science and planning can save lives. First, the monitoring network. Mount Rainier is one of the best watched volcanoes in the world. A dense array of instruments keeps constant vigil. Seismometers detect even tiny earthquakes in Rainier's vicinity. GPS stations and electronic tilt meters measure the mountain's shape to the millimeter. Gas and hydrothermal sensors track any change in the volcano's steaming innards. Even the National Park Service maintains webcams and river gauges in case the unexpected happens. In short, any sign of unrest, magma moving, glaciers shaking, or even gas surges will be noticed. Then there's the lahar detection system. Buried along the Puyallup floodplain are acoustic flow monitors, AFMs, essentially geophones tuned to the signature of a passing mudflow. When those pick up a lahar, an automated system immediately triggers sirens and alerts. Pierce County's network of outdoor sirens, mounted on poles and rooftops, will then wail at top volume, instructing everyone to evacuate the valley. These sirens were designed specifically for volcano emergencies. In a real event, they will wail until the batteries die or they are destroyed, so they won't cut off until people have had time to flee. Beyond hardware, there is land use planning. Since the 1990s, Rainier's historic lahar paths have been mapped into hazard zones. These maps are now used by cities and counties when approving new development. For example, many areas where people have built are now designated no-build zones or require extra precautions. Even before an eruption, this guidance limits how much can be built directly in the highest risk corridors. And of course, education and drills form the human side of preparedness. Schools in lahar zones run regular evacuation drills. On March 21, 2024, more than 45,000 students participated in the largest drill ever held. They practiced walking or busing to high ground, simulating a real lahar warning. Emergency managers turned entire cities into game boards. For a morning, buses, fire crews and volunteers all executed what to do if 30 minutes were all the time available. Year after year, these exercises demonstrate that foot evacuations and planning can work even in a short time. Community workshops, school lessons and public signage like bright lahar route arrows keep the awareness alive. In this hazard map, the coloured areas show where lahars and debris flows could inundate Rainier's valleys. Communities like Puyallup and Orting sit in these zones, but now every town and school board has access to maps like this. In Pierce and King County, some roads are marked evacuation routes to high ground. Others are off-limits during lahar emergencies. Even smartphone apps can pinpoint if you're in danger. All these efforts, the earthquake and flow monitors, the sirens, the evacuation plans, the hazard maps, are the tools science provides. They are not perfect protection, but they greatly reduce risk. When a real event comes, it's preparation rather than panic that can make the difference. The next great lahar from Mount Rainier may happen next year. It may not happen for another 1,000 years. No scientist can honestly predict the date. But geology doesn't work on human schedules. The evidence is already beneath our feet. The valleys surrounding Rainier were shaped by enormous mud flows that happened again and again across thousands of years. Every buried forest, every layer of volcanic clay, and every ancient boulder field tells the same story. This mountain has already shown us exactly what it is capable of. That is why emergency planners continue running drills. Why scientists monitor earthquakes around the clock. Why sirens stand ready in quiet communities that may never hear them. Because if the next collapse begins, there may be only minutes to act. Tomorrow morning, school buses will once again cross the bridges beneath Mount Rainier. Hikers will photograph its glaciers. Families will picnic along rivers that once carried walls of mud. The volcano will appear as calm as it has for centuries. And that is the final paradox of Mount Rainier. America's deadliest volcano doesn't need to erupt. Sometimes all it has to do is fall apart.